Welcome to the course Business Analytics and Text Mining Modeling using Python. So, in previous lecture we had started our discussion on an NLTK package that is typically used for text mining modeling or text analytics, and also in NLP, natural language processing. So, what we will do, we will go through, we will do a small recap of few steps that we discussed in the previous lecture, and then we will pick up from the point where we stopped in the previous one. So, let us start. So, first thing as we discussed is NLTK package. So, first thing we need to import this into the Python environment, and NLTK is typically installed, comes with the Anaconda distribution. This aspect we discussed in the previous lecture. Then also certain NLTK resources we would be requiring as part of our discussion of this package, and text mining modeling as well. So, this part we had done in the previous lecture itself. So, I have commented those commands here. So, let us move forward. So, next thing that we were able to cover in the previous lecture was the Brown corpus, and we went through some of the initial lines of code which we typically perform while trying to understand the corpus, the kind of files that are there, the kind of text that is there. So, let us quickly go through this part as well. So, a Brown corpus part of NLTK corpus module. So, we will import this one also, and then categories. So, typically if you just if you have a look at the kind of corpus, this is a categories based text corpus. So, if we look at the categories in the corpus, like we discussed in the previous lecture, that you can think about a tree kind of a structure and categories and files under those categories. So, these are the categories, and we looked at the first 5 sentences also. So, you can see this is how this is going to look like. First 5 sentences, this seems to be a list of strings, and we can always use join method that we learned before in our previous previous lectures, and we can have a nicer look of sentences there. Then if we are interested in text from a particular particular category, so that also we can perform. For that we can use the categories argument here. So, we can run this also and have a look at the 5 sentences there, and then if we are interested in finding out the files that are part of that corpus. So, for that we have this file IDs method that can be used. So, you can see this this particular method we can call on the corpus, and we will have the list of files that are part of the corpus. So, if we are looking to find out the files or file IDs under a particular category in the corpus, so that also can be done. File in the file IDs method we can use this categories argument, and we can find out the files that are part of that particular category. So, you can see here again output. Now, if you are interested in a particular file, let us say CA18 here. So, we can use the file IDs argument here in our brown.sends. So, sends method we can specify the file ID, and the text from that particular file ID is going to be produced in the output, and then we can use the join method to merge that those sentences, and let us have a look at 5 sentences from this file. So, you can see this text. How we are able to obtain this from a particular file in the corpus. Now, we were able to discuss up to this much. Now, we will pick up another corpus, Gutenberg corpus, and we will repeat some of the previous kind of lines of code, and then we will move forward. So, first thing, let us load the Gutenberg corpus here. So, from nltk.corpus import Gutenberg here. So, we will have this. Then as we did for the Brown corpus, here also using the file IDs method, we can have a list of the files that are there. So, if I run this, you can see, you can have a look at the file, all text files, simple text format files. So, we talked about various file format for textual data. So, you can see in this particular corpus, all these files that we can see, they are in the simple text txt format. Now, let us move forward. Now, let us talk about raw method that is there. So, this method can be used to return a single string for the file. So, all the textual content that is there in the file can be returned in a single string object. So, let us pick up one file. So, we are picking here this austin-emma.txt file out of the the list that we just saw in the previous output, and we are using file ID's argument here for the raw method, and we are passing on this file name, and what it will do, all the text content it will be defined in this single string object Emma. So, let me run this and we will have Emma. So, let us have a look at the total number of characters that are part of this particular string object that we have just created. Remember, this string object is representing the whole content in this particular file austin-emma.txt. So, if I run this, so you can see that in the output 80 here 8,87,071 characters are part of this textual content that is there in this particular file here. Now, we can have a look at, because now this is a string object. So, we can have a look at let us say first 200 characters in this particular file. So, Emma, and we can use, as we have learned, we can use this brackets and colon notation to actually access these characters here. So, if I run this, you can see in the output 81 those 200 characters we are able to see. So, you can see here. Now, if you want to have a nicer output here, so you can always use this print function. So, we can pass on this string Emma and brackets 0 to 200 to print function, and we will be able to print a nicer output here. You can see now this is more like a text format kind of output. So, slightly better to understand the kind of content that is there. Now, let us move to the another important aspect here. So, in previous lecture we talked about the tokenization as one of the important steps. We talked about certain other steps, and we also discussed that order of execution of those steps depend on the problem and the data. So, we will be discussing we will be discussing some of these steps one by one, and orders are typically, as we said, is going to be depending on the kind of modeling that we are going to do. So, we will first pick up the sentence tokenization. So, typically as we discussed, two types of tokenization are done, sentence and word tokenization. So, we will start with the sentence tokenization. So, this will do using different NLTK interfaces. So, different ways we can actually perform this sentence tokenization. So, we will take some of those examples here. So, let us pick up first approach. So, in this approach we use this sent_tokenize function to perform tokenization. So, typically this is the default and a recommended sentence tokenizer. So, if you do not have any other peculiarity in your problem or data set that you are dealing with, the text corpus that you are dealing with, then you can always go with this recommended sentence tokenizer. So, this particular tokenizer advantage with this one is, this is a pre-trained tokenizer on several language model, not just English, and it can work really well on many popular languages. Now, one thing is important to understand here, these that many of these libraries, they are pre-trained on European language, English and other European language, and other languages coming from Western countries. So, they might not work so well for Indian languages. So, let us move forward. So, NLTK.sent_tokenize. So, Emma is the string object that we have there. So, we will pass on this one, and using this we will get our sentence token in this. So, let me run this. Now, let us have a look at the number of sentences here. So, we can use the length function here and Emma_sends, and you can see we have 7,493 sentences here. Let us have a look at the first 5 sentences. So, again we can use Emma_sends, and we can use this brackets colon notation 0:5, and we will have the output here. Now, here if you look at the output, few things you can notice here, that the tokenizer, the just now that we have used to produce these sentence tokens. So essentially, as we talked about, we are as we talked about about sentence tokenization, is that breaking the text into sentences and in using word tokenization into words. So till now what we are doing is we are breaking the textual content into sentences here. So if you look at the output that is there in this output 85, typically the tokenizer, it will not just use periods to delimit sentences. It will also consider other punctuation and the capitalization of words also, because capitalization of words, any new sentence is supposed to be starting with a capitalized word. First character is first character of the first word in a sentence is going to be in the capitalized form. So that can also be used by this tokenizer, and not just the periods, other punctuation marks can also be used to tokenize sentences. So if you look at this first sentence, it starts like Emma by Jane Austen, and you can see, and now you can see the second sentence starts with she was the youngest of the two daughters, and the third sentence her mother / Anne had died. So in fourth sentence 16 years had, and then the fifth sentence between them. So if you really look at here, then different if you look at the full output, then you will find many places the capitalization and other things have been used. You can see all these sentences, the first character of the first word in all these sentences in the is capitalized there. So that is also there, and dot is also there at the end of each of these sentences mostly. So you can see that all these things are being used by tokenizer to produce these sentence tokens. So this is first approach. Now let us talk about the second approach here. So in this approach, we use this punct sentence tokenizer class to actually perform tokenization. So the previous function that we just used, sent underscore tokenize function, that is also an instance of this class punct sentence tokenizer. So instead of using this pre-trained or rather well trained send tokenize send underscore tokenize function, we can have create another instance of this class and maybe use that. So this could be another approach. So for this we will initialize another instance here. So punct underscore st, because this is for we are working with for sentence tokenization, nltk dot tokenize, and this class punct sentence tokenizer. So we will have this instance here. So let me run this, and then we can call this instance punct underscore st, and we can use this tokenized function here, pass on Emma, and we will have our tokenization performed here. So we will have Emma underscore sends 2. Now here also we can again have a look at the output for first 5 sentences. So Emma underscore sends 2 0 to 5 within brackets 0 colon 5, and you can see the output here. You can also compare the output here. You would see that mail output is similar to the output 1, that is using the default sentence tokenizer function. There might be slight differences here. So if you just compare, you can see this that sentence starting of sentence for few sentences slightly different. You can see 16 years is fourth sentence there in output 85, then between them is fifth sentence. If you come here, then slightly different thing, 16 years is there, then Woodhouse's family. So the fifth sentence is actually starting from slightly different there, Woodhouse's family. So maybe some punctuation mark has been used differently, because the other one, the other tokenizer was pre-trained, and so it might work differently. So there you can see Mr. Woodhouse family here, and so from that from that capitalization maybe the default tokenized function tokenized method has picked up and perform the sentence tokenization. So, you can see output is more or less similar, but there are certain slight differences that you can notice here, and the differences is also mainly, as I said, is because the default tokenizer is actually pre-trained. So, it is working differently than the class, and if we take the class create an instance and use the method there. So, let us talk about the next approach that is third approach for sentence tokenization here. So, in this we can use an instance of regex tokenizer class. So, this is based on regular expression. So, we have touched a bit upon regular expression in previous lectures. So, here we would be specifying a particular regular expression, and we will use that to find out patterns, and that is going to be used to create a sentence tokens here. So, we are going to using an instance of regex tokenizer class, and specific regular expression based patterns are going to be used. So, you can have a look at this pattern here. So, this pattern is mainly to capture any sentence and different components. There could be different components of a sentence. So, you can see within parentheses we are trying to capture some of those aspects here. So, overall this pattern is about identifying sentences there. So, this pattern would be able to able to select able to match most of the sentences using this pattern. So, let me run this. So, we will have this pattern 1. Now, we can use this regex pattern for building the tokenizer, and here you would see in the function that we are going to call here tokenize.regex exp tokenizer. Here we have two arguments, pattern and gaps. So, pattern we have already defined. So, we will use the pattern 1 and gaps is true. So, if this gaps is true, then will this particular method is going, this particular function is going to use this to find gaps between the tokens. So, let me create this instance of this regex object here. So, we got a class, we got an instance of this class regex object here. Now, we can use this regex underscore st that we have just created and call this tokenized method here, where we will pass on emma the same text here, and we will have the tokenization in emma underscore sends 3. So, let me run this and let us have a look at first 5 sentences. Now, you can again compare the output. Now, you can see that first sentence starting if you look at the character by character, overall the output is similar to the output 1 and previous output as well. However, if you look character by character, slight differences are going to be there. So, you can see there Emma started with brackets, so that thing is there still. If you look at second sentence, you can see before in the second sentence before C we have the slash n also here, but in the previous output we did not have that, and we go back further and in the default tokenizer output also started with C. So, we can see that slight differences here because of the approach. Certain output certain changes, certain differences would always be visible there. You can see in next line also her mother, before her mother there is a space hanging out there, and the 16 years again it is prefixed by slash n, and so because of the we are using a pattern to match the sentences. So, these kind of slight changes are going to be there in this. However, this is another approach to create sentence tokens. Now, let us move forward. Now, next thing that we are going to talk about is word tokenization. So, for word tokenization as well we will be using a number of analytic interfaces. So, we will be talking about a few approaches here. So, let us start with the first approach. So, in this also for word tokenization also we have a default and recommended word tokenizer. So, that is word underscore tokenize function. So, that is typically used to perform word tokenization. So, for word tokenization as well, we can call this function word underscore tokenize, and we can pass on this string object emma here, and we will have the word tokens in emma underscore words. So, let me run this default tokenizer for words, and let us have a look at the number of words here. So, we can use the length function here, length, and within parentheses emma underscore words, and you can see in the output 94 that we have 1,91,785 words here. So, those many words are there in this word tokenization output that we just perform. If you understand looking at, let us say, first 500 words. So, let me run this emma underscore words and within brackets 0 colon 500, and we will have, you can see the output. Now, this is word tokenization. So, you can see different words we are able to see. In the sentence tokenization we had the sentences there. Now, this time we have the words here. So, you can see even the first opening bracket is also being treated as a word token. Then the next one is Emma, then by, then Jane, then Austin 1816, then again closing bracket here. So, in this fashion you can see after Woodhouse we have comma here. So, comma is also being treated as a token here, then again comma, and all those instances or instances per comma is going to be repeating. So, you can see the kind of output that is that we are able to obtain by using the default word tokenizer. So, even the different special characters and punctuation marks, they are also being treated as a tokens here. Now, let us talk about the second approach. So, here for the second approach we can use this tree bank word tokenizer class to perform tokenization. So, this particular class is actually based on the pen tree bank, and it internally it uses various regular expressions to tokenize the text. And in this one primary assumption is that the sentence tokenization has already been performed. So, actually it is going to be typically used to tokenize the sentences into words. So, let us take for an example, let us take the first sentence that we had obtained by applying the default sentence tokenizer. So, we will take emma underscore sends 0. So, let me run this. We will create an instance of this tree bank tokenizer, tree bank word tokenizer, and also this is the sentence that will be that we can take for applying this. Let us have a look at emma underscore sends 1 also. This is the second sentence that we have. Now, we can use the tokenize method here. So, we can call tree bank underscore wt, the instance the class instance that we just created, and call the tokenize function here emma underscore sends 0, and if I run this we will have it will return word tokens. So, you can see now we can have a look at the, let us say, first 500 words here. So, if I run this you can see here similar to output 2. So, you can see in this also output 99 also first token is opening bracket, then Emma, then by Jane Austen 1816, and then closing brackets. You can also see commas there also. So, similar kind of output that we have obtained. The difference is that this is an instance of a different tree bank word tokenizer class, and it is typically used to convert sentences into word tokens. So, a few more things that this tokenizer, this splits and separates into independent tokens some of these things, periods appearing at the end of sentences. So, in the default tokenizer that might not be there. In case you will also find periods appearing as tokenizer. If you just scroll down in this output also you might find, you can see semicolons, we can already see and dot is also there. So, periods as independent tokenizer we can obtain using this in this tokenizer. Commas and single quotes when followed with white spaces. So, some of these tokens are common with the previous output as well, but this particular tokenizer will do it also. Most punctuation characters that might not be the case in the default tokenizer. Words with the standard characters. So, they can also be the tokenizer. Standard contraction, standard, for example, don't, do and n apostrophe t. So, don't might be broken into these two words, and these two tokens might be there. So, slightly a different behavior. So, mostly output is going to be same, but few differences might be there. Now, let us talk about the third approach. Now, this is an instance of regex exp tokenizer class, and here we use a specific regular expression based patterns. And so, let us take an example pattern to identify tokens. So, here we are defining this pattern to \w plus. So, this is something that we are going to use to identify words from the text that we have. So, let us first create a let us first create this pattern 2 object here. So, let me run this, and then using this pattern 2, and you can see gaps is false, and we will be creating this regex underscore wt object. So, let me run this, and from this we will be creating this emma underscore words 3. So, we will tokenize, we will call regex underscore wt dot tokenize, and we will have pass this emma, and this will return us the tokens using the particular regex object, and therefore, the pattern. So, if I run this, and let us have a look at first 500 tokens here. So, you can see here output. So, output is similar, but slight differences you can notice immediately. For example, the earlier two outputs we had opening brackets also as a token. In this case, that is gone because of the regular expression that we have used. So, we did not consider that as a token. So, that is gone here. You can also see certain other punctuation marks which were treated as tokens in the previous two approaches. Now, they are also gone. So, depending on, so these are different approaches that can be really useful depending on the problem that we are dealing with and the kind of text corpus we might have. So, you can clearly see that in this particular example typically meaningful words are there as tokens. Now, we can have another pattern 3, where this one we can use to identify gaps. So, again let me define this pattern object pattern 3, and we will have another regex object here regex underscore wt1, and we will call this this class function regex p tokenizer and pattern 3 and gaps true in this case. If I run this, and we can use now this one to tokenize emma, and let me run this, we will have emma words. Let us have a look at the first 500 let us say tokens here. So, this is if you look at this output and compare with the previous one, now you can see earlier in the previous one we did not have opening brackets as the token. Now, here opening bracket has been combined with emma here. So, that is because of the the pattern that we changed the pattern, and therefore, the output in terms of word tokens that we are getting, that is also changed. So, this is another approach. So, let us move forward. Now, in this we can also, using the previous output that we had regex underscore wt1, we can also get a start and end indices here of each token. And so, for this we can use this span underscore tokenize method, and we can call on this regex object regex underscore wt1 dot span underscore tokenize and pass on emma, and we will have the start and end indices of each of those tokens. So, let us say clever start index value for C and end index value for R. So, in this fashion, for all of those tokens we will get those indices and list of indices. So, let me run this, and let us have a look at those indices, you can see 0, 5, 6, 8. So, in a sense you are you will get the kind of idea, the kind of number of characters that are part of those tokens, and you can use this also to construct the tokens here again, or even modify the tokens here again. So, we can use this list comprehension here, mi start colon end, and for a start comma end in word indices. So, in this fashion we will be able to produce the a kind of similar output here that we had. So, using a start and end indices also, you can clearly see that we have been able to produce the same output, because it is coming from the same approach, only the different functions, combination of functions and code that we are using here. So, you can see the previous output that we had, and here the tokens, you can see first token mi, it had the opening brackets also. So, in this case that we are where we are using start and end indices, here also you can get the similar output. So, we will like to stop here, and in the next lecture we will continue to discuss about word tokenization using another approach, fourth approach. So, let us stop. Thank you.